All right, so today we are going to be talking about the Rossby numbers, the first thing we're going to talk about. And this is a non-dimensional parameter or a non-dimensional number. And it sounds scary, but it's not. It just means that it doesn't have any units. And we use it to help us determine what terms we need to consider when we're looking at the different equations that affect the motion in the ocean. And we'll get to looking at those in more detail as we keep going. But we're going to start by looking at this Rossby number. And then we're going to look at edge waves. So we're going to start to look at some really cool waves because this week we are going to be doing our waves lab. So we're going to look at some unique waves. And the first one, we'll start with our edge waves or trapped waves. And then we'll look at some waves that are long waves. And so they are actually affected by Coriolis, including Kelvin waves, Poincaré waves, and Rossby waves. So to get started, I'm going to go back over this again, the coordinate system that we use in the earth sciences. So this plane here, this square that we have here, if it's not moving at all, this would be the F-plane approximation. And so in that case, we say that the x direction is the east, is positive in the east direction, negative in the west direction. It's called the zonal direction. The velocity in that direction is dx dt equals u, and so the acceleration will be du dt. Then the north-south direction is our y direction, and that's called the meridional direction, and the velocity is dy dt, and that's equal to v, and the acceleration will be dv dt. And the up vertical direction is our z direction. So the velocity is dz dt, gives us w, and so our acceleration will be dw dt. And of course, our Earth is actually spinning, even though we like to consider just this flat, unmoving square. And today we'll also talk about what would happen if we consider that on our flat square, if we consider that instead of Coriolis being constant, that Coriolis is actually changing as it is. And we'll look at that here in a little bit. All right, so consequences of Coriolis. For an object with an east-west or zonal velocity u, we're going to get a Coriolis acceleration in the north-south direction or the y direction, and it'll be negative f times u. For an object with a north-south meridional velocity, v, the acceleration will be f times v in the east-west or x direction. And so we can say the y component, which if we think about it in terms of how you've seen other physics problems, that would be the acceleration, the y component of the acceleration will be equal to negative f times u. I don't have this on this slide, but I'll add that to it really fast here. The other thing we can think about is, in that case, we can then say that this, if there can be other terms as well, but if there are no other terms, then we can say that in the y direction, this will be dv dt, and in the x component will be that in the acceleration. So the acceleration in the x direction will be f times v, and so that will be in the acceleration in the x direction will be du dt. And we see that this f here, the f is our Coriolis parameter. It's equal to 2 omega sine theta. And we found out omega is 2 pi over 24 hours, basically, or the sidereal day, more precisely. And that's 7.29 times 10 to the minus 5th radians per second. And theta is latitude. So if we have, so what we see is that that term, the Coriolis parameter, actually increases with increasing latitude. So when we have 0 degrees at the equator, f will be equal to 0. And at the North Pole, sine of 90 degrees is 1. So at the North Pole, f will be equal to 2 omega because we'll have sine of 90 degrees is 1. So we'll just get 2 omega. And at the South Pole, we'll have negative 2 omega. So when we look at theta in terms of if it's south latitude, it's a negative value. So we'll end up with a negative f. Now we notice that in this case, if we have a change in f, it changes in the north-south direction. And so we can write that as the change in f over the change in y. And this is what we call beta. And so beta here is equal to df dy. It's the change in the F parameter in the Y direction. And we'll talk about why that's important later. All right, so that's Coriolis review. Now we started to talk about this idea of an inertial current. So an inertial current, the idea is if something starts the water in motion, and we'll look in more detail about how we can start the water in motion. We talked about that a little bit with waves. And then stops pushing on it. So first we have a force that starts the water going, and it gives it some inertia. So it has mass already because it's water and it has mass, and we give it some velocity. So now it has inertia. So it's moving and there's nothing acting to stop it because there's not a lot of friction. We usually consider almost no friction. So the only force acting on it in that case will be Coriolis. And so we saw that if we have our example that we've been looking at, we have our water parcel moving in the east direction, there will be a Coriolis force down in the south direction. Now it's only perpendicular because Coriolis is only acting at right angles. So it's not going to affect the magnitude of the velocity. It's just going to affect its direction. And so now our velocity will turn a little bit, and it will turn to its right or down towards the south in this example. And now it still has a velocity, so it will have Coriolis acting on it, proportional to the velocity at 90 degrees. And so it will act again to its right, and we'll make our velocity vector move again, and so on and so forth as it continues being acted on only by Coriolis. If our water parcel is acted only by Coriolis, it will continue just moving around to its right in the northern hemisphere. For example, in the northern hemisphere. The southern hemisphere will be moving to the left. And so we see that we end up with a circular motion. And those are what we actually see in the ocean. These are inertial currents that we see all the time. So we saw that if the only force acting on our water parcel is Coriolis, then in the x direction, the Coriolis acceleration, written as a sub x here, is going to be equal to F times v in the east-west or zonal direction, or the in the x direction here. And so the x component, of the force will be F sub x will be equal to mass times the acceleration in x. And so that will be equal to mass times F times v. So that will be the x component of the force. And then in the y direction, we'll have the Coriolis acceleration in the y direction. That's equal to negative F times u. And that's in the north, south, or meridional direction. Again, that's the y direction here. And so the y component of the force will be Fy equals mass times the acceleration in y, which will be equal to negative mf times u. So if we go then and we just look at, is there a question? All right. So if we just look at what happens with the Coriolis turns our water parcel. So it moves in a circle, as we just saw. So it has a centripetal force. So that centripetal force is going to be F centripetal is equal to mv squared over r. So that means that in the x direction, the sum of the forces in the x direction must be equal to mv squared over r because it's moving in a circle. So since the only force acting on the water parcel is Coriolis, that means that our force balance tells us that the sum of the forces in the x direction is just Coriolis. So it's the mass times F times V, that's Coriolis. And that must be equal to the centripetal force, mass times V squared over R. Now we can go ahead and divide through by the mass, and that'll give us the acceleration in the x direction. And so we see that the acceleration in the x direction will be Fv equals v squared over r. And so based on that, we saw that the period of the inertial currents, the acceleration must come from the only force acting on the water parcel. So the acceleration is in the x direction. And so we get v squared over r equals F times v. We can go ahead and divide through one of these v's and multiply through by r. And so if I multiply through by r, I'll get v equals F times r. And so v equals F times r. So the period we know is equal to the circumference over the velocity. So the circumference is 2 pi r over v. We can then plug in r times f for v. And so now our period is 2 pi r over r times f. So r's cancel. And we'll see that the period is 2 pi over f. Okay, and then we saw that we had our inertial currents. And so they rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And the period is equal to 2 pi over f. Now, we went through that yesterday and you found a couple different inertial currents. Now I want to remind you that we started talking about Coriolis and we saw that the first thing that ever showed us that there was Coriolis was Foucault's pendulum. And so if we have a pendulum on the Earth, it will rotate, and it will rotate even though it's just moving back and forth. So it's just moving back and forth, but because if we watch it, we'll actually see that the pendulum itself looks like the pendulum is rotating because in fact, the Earth is rotating beneath it. And so we saw that, and we found out that the period of the Foucault pendulum was equal to 12 hours over sine of theta, where theta, and again, this was hours. I remember that was confusion. 12 hours. It was written that way in the book is just an H. I know a lot of us use HR over sine of theta, where theta is the latitude. Okay, so yeah, you did those. Okay. So now comparing these, we saw that the period of Foucault pendulum and of the inertial currents is 12 hours over, the period of a Foucault pendulum is 12 hours over sine theta. And we know the period of the inertial currents is 2 pi over f. Where f equals 2 omega sine theta, and omega is about 2 pi over 24 hours, and theta is our latitude. So I want you to calculate, first of all, how long will it take the pendulum at 45 degrees south? So I want you to think about south this time to rotate 180 degrees. So that is swinging in the initial plane. And I want you to think also then calculate the period of rotation for an inertial current also at 45 degrees south.